to the ACE Engineering Academy online platform. Dear friends, today in this platform we are going to discuss the most important subject for the mechanical engineers, that is thermal engineering. Dear friends, this subject is very important for those students who are going to prepare for the TSPSC AEE exam, and it is also equally important for the TSPSC AE exam and AMVI exam. Okay, and it is also useful for the APPSC AEE exam and AE exam. Before going to start, the most important questions for the most important subject, that is thermal engineering. Dear friends, I am Malakondaiah Sir, faculty at ACE Engineering Academy. Dear friends, my hard work and more than 25 years of experience and blessings from parents and gurus elevated me for teaching almost all thermal oriented subjects from basic level to high end level. Dear friends, we have divided the thermal engineering into three parts, namely basic thermodynamics, power plant engineering and internal combustion engines, similarly refrigeration and air conditioning. We have discussed the most important questions for the very first part, that is basic thermodynamics, on 20th of this month. On 20th of this month, we have discussed the most expected questions for the basic thermodynamics. Today, we are going to discuss the most important questions on the syllabus for the subject power plant engineering and internal combustion engines. Before going to start the questions, let us see the syllabus from the power plant engineering and internal combustion engines. Dear friends, you have only, you means the students who are preparing for TSPSC AEE exam under power plant engineering, only three topics are there, namely reciprocating compressors. You need not to prepare all the compressors like Roots blower, axial flow compressor, the centrifugal flow compressor, etc. Just basic part of compressors, that is reciprocating compressor. Similarly, the second topic is Rankine cycle. As we all know, this Rankine cycle is the critical cycle for thermoelectric power plant. Similarly, the third topic is Brayton cycle. This Brayton cycle is the ideal cycle or theoretical cycle for gas turbine power plant. Okay? Only these three topics you need to prepare under power plant engineering: reciprocating compressors, Rankine cycle and Brayton cycle. Okay. Similarly, under internal combustion engines, again there are three topics given, namely air standard cycles, combustion in spark ignition and compression ignition engines. The third one is performance and testing of internal combustion engines. Only three topics need to prepare under IC engines. Okay. Now let us see the weightage. Look at the weightage which were asked in the year 2015 for AEE exam, the same year AE exam, etc. From the power plant engineering in the year 2015 for the exam AEE, 12 marks were asked. Okay. From the IC engines, 8 marks. Total 20 marks. That is the weightage of this beautiful subject. Similarly, for the AE exam conducted in the 2015, 6 marks were asked for power plant engineering and 10 marks were asked from internal combustion engines. Okay. Similarly, for the HM WSSB, this board asked 6 marks from power plant engineering and 10 marks from internal combustion engines. Similarly, in the year 2020, the board asked 8 marks from the power plant engineering and 4 marks from the internal combustion engines. From this, it can be evidently concluded that around 15 marks can be expected from these two subjects. Okay. Now let us see the reference books. Dear friends, the best material for both TSPSC and APPSC for both AEE and AE is our academy material, ACE Academy material. Dear friends, we have prepared the best questions for the both APPSC and TSPSC AEE and AE exams. Of course, this material is also useful for the AM VI students. Okay. In addition to this material, you can also go through the objective question bank mechanical engineering by a panel of experts, Aroma Publishing House. Similarly, the other kind of material, mechanical engineering objective by DS Kumar. Dear friends, among these three materials, I personally refer the first one, that is our academy material. Having this introduction, now let us see the most expected questions for power plant engineering and IC engines. Look at the very first question. Try to read the question clearly. Question reading is very, very important. Try to read it. It is asked like this. Consider the following features for a gas turbine plant. Gas turbine plant means indirectly for Brayton cycle. Intercooling, regeneration, reheating. Which of the above features in a simple gas turbine cycle increase the work ratio? These are the methods for improving the performance of the gas turbine power plant. Among these three methods, what are the methods for increasing the work ratio? That is the question. Look at the options. Different options are available for you. Now let us decide the correct option. First let us take the intercooling. Intercooling, intercooling is mainly used for decreasing the work input to the compressor. Decreasing the work input to the compressor. Decreasing the, should be very careful, decreasing the work input to the compressor. But what about the turbine work? Dear friends, remember the turbine work remains constant. Okay. Then as you know, the work ratio equal to ratio between the net work and turbine work. This net work equal to turbine work minus compression work dividing by turbine work can also be written as 1 minus compression work dividing by the turbine work. The intercooling is decreasing the work input to the compressor at constant turbine work. Then what is happening? This factor is going to decrease. Once this factor is decreasing, 1 minus decreasing value will increase the work ratio. From this you can conclude that the intercooling mechanism can increase the work ratio. Okay? Similarly, the second mechanism is regeneration. As you know, the regeneration main intention is to minimize the heat input to the cycle. The regeneration main intention is to minimize the heat input to the cycle. What about the turbine work and compression work? Turbine work remains constant. Of course, compression work also remaining constant. If these two are constants, what about the net work? Net work equal to turbine work minus compression work. Since turbine work and compression work both are constant, this net work also remaining constant. Okay? Then what about the work ratio? Work ratio equal to ratio between the net work and turbine work. Since turbine work is constant, net work also constant, therefore there is no change in work ratio with regeneration mechanism. Okay? Similarly, look at the other mechanism, reheating mechanism. This regeneration does not increase the work ratio. This intercooling increasing the work ratio. Now look at the reheating mechanism. As you know, reheating main intention, reheating of the gas turbine power plant. The intention of the reheating for the steam turbine power plant is differing from the intention of reheating for the gas turbine power plant. The reheating for gas turbine power plant main intention is to increase the turbine work output. To increase the turbine work output. But what about the compression work? Compression work remains constant. Okay. The work ratio equal to 1 minus compression work by turbine work because of the increase in turbine work at constant compression work. You know, this factor is decreasing. 1 minus decreasing value will increase the work ratio. So reheating is increasing the work ratio and intercooling also increasing the work ratio. Okay. Now let us see the options. Reheating is increasing the work ratio and intercooling also increasing the work ratio. Therefore, you can select 1 and 3. Look at the 1 and 3. Only 1 and 3. Option D is absolutely correct. Is it understood clearly? Yes. Now let us see the another important question. Try to read this question. Try to read this question. It is asked like this. Use of maximum pressure ratio corresponding to maximum to minimum cycle temperature ratio. Generally, maximum temperature for gas turbine power plant is marked with T3 and minimum temperature is T1. It is given that corresponding to maximum to minimum cycle temperature ratio. This temperature ratio remains constant. Okay. In case of Joule cycle gives which one of the following? That means for the constant maximum temperature dividing by minimum temperature ratio, if you use the maximum pressure ratio, what will be happening? That is the question. Okay. It is given for the Brayton cycle. You know, Brayton cycle other name is Joule cycle. As you know, the Brayton cycle efficiency is equal to 1 minus 1 by pressure ratio power gamma minus 1 by gamma. Isn't it? Now, if I increase the pressure ratio, what is happening? This whole factor is decreasing. When this whole factor is decreasing, 1 minus decreasing value will increase the Brayton cycle efficiency. Okay? It means if the pressure ratio increases, definitely the Brayton cycle efficiency increases. Okay? But look at the options. Look at the first option, maximum efficiency but very less specific work output. We have decided the efficiency by increasing the pressure ratio, definitely efficiency can be increased. For deciding the net work output, let us project the temperature versus entropy coordinate system. Temperature versus entropy coordinate system. Corresponding to compression ratio, let it be Rp equal to 10. As you know, the temperature after compression T2 is equal to T1 into Rp power gamma minus 1 by gamma. Corresponding to pressure ratio 10, the Joule cycle or Brayton cycle may be looking like this. 1 to 2 reversible adiabatic compression, 2 to 3 constant pressure heat addition, 3 to 4 reversible adiabatic expansion, and 4 to 1 constant pressure heat rejection process. So that is the Brayton cycle. For the pressure ratio, let it be 10. For this cycle, where do you find the maximum temperature? Maximum temperature is found at state 3. T3 will be the T maximum. Dear friends, remember that maximum temperature completely depending on metallurgical limitation of the material what we are selecting for gas turbine bleeding system. Assume the metallurgical limitation for the gas turbine bleeding system is around 1500 Kelvin. That means you should not operate the gas turbine power plant with a temperature more than 1500 Kelvin. Okay? Now, when I increase the pressure ratio, listen carefully. When I increase the pressure ratio from 10 to 20, look at the temperature after compression. Temperature after compression T2 dash equal to T1 into Rp power gamma minus 1 by gamma. Corresponding to pressure ratio 10, look at the temperature after compression. This is the temperature after compression. Okay? Now, amount of heat can be added is equal to Cp into T3 minus T2. Okay, but when I increase the pressure ratio, from 10 to 20, the temperature after compression increases. The temperature after compression may be marked like this. This is the 2 dash, that is the state of the gas after compression with pressure ratio 20. The temperature after compression is T2 dash. Then you can add the heat like this. This is the heat addition process, 2 dash to 3 dash. Now 1 to 2 dash is the isentropic compression. 2 dash to 3 dash isobaric heat addition. 3 dash to 4 dash isentropic expansion. From the diagram, it can be concluded that if pressure ratio increases, the compression work increases, because corresponding to pressure ratio 10, work required for compression equal to Cp into T2 minus T1. Whereas with pressure ratio 20, the work required for compression is Cp into T2 dash minus T1. That means indirectly, if I increase the pressure ratio, the compression work is increasing. Okay? If compression work is increasing, what about the net work output? Net work output is also called specific work output. Means per kg of the working material is equal to turbine work minus compression work. Because of the increase in compression work, the net work output is decreasing. That means when you keep on increasing the pressure ratio, the compression work is increasing further and further. It is like this. If you maintain the pressure ratio Rp equal to 50, corresponding to pressure ratio 50, the temperature after compression, right? The temperature after compression will be more than T2 dash. This may be the 2 double dash, where the temperature is T2 double dash. Corresponding to that compression temperature, this is the heat supplied process. Then the expansion is proceeding like this. This is the 3 double dash, 4 double dash. From this you can conclude that when you keep on increasing the pressure ratio or compression ratio, compression work is keeping on increasing. By the time the compression work is keeping on increasing, definitely net work output decreases. So from that, the moral is, when you keep on increasing the pressure ratio, thermal efficiency may be increasing, but net work output is decreasing. Okay. Now look at the options. Try to look at the first option, maximum efficiency but very less specific work output. Yes, when you keep on increasing the pressure ratio, efficiency is increasing but the specific work output decreases. Therefore, option A is absolutely correct. Okay. Shall we move to the next question? Yes. Look at the next question. Try to read it clearly. The enthalpy of steam entering a turbine in a Rankine cycle is 3200 kilojoules per kg. That means the steam is entering to the steam turbine with 3200 kilojoules per kg. The enthalpy after isentropic expansion is 2400 kilojoules per kg, and the enthalpy at the end of actual expansion is 2560 kilojoules per kg. Then what is the turbine efficiency? For that, it is better to mark the Mollier diagram, can also be called as enthalpy versus entropy diagram. As you know, with HS coordinate system, the saturation dome is appearing like this. That is how the saturation dome is appearing. This is the critical point. Okay? As you know, by the time the steam is expanding over the steam turbine blades, the pressure of the steam is dropping from P1 to P2. The pressure before expansion is P1, after expansion is P2. Okay. Generally, we are allowing the superheated steam to the turbine. The superheated temperature of the steam may be T1. Wherever the P1 and T1 are meeting, that is the initial state of the steam, where the enthalpy of the steam is H1. Look at the H1 value. The steam is entering with an enthalpy 3200, 3200 kilojoules per kg. Okay. Now, theoretically, the expansion is happening isentropically like this. This is the isentropic expansion. I am marking the state 2 at the end of isentropic expansion. Now look at the enthalpy of the steam after isentropic expansion. The enthalpy of the steam after isentropic expansion is H2. The enthalpy of the steam after isentropic expansion given 2400 kilojoules per kg. But it is given the enthalpy after actual expansion. The actual expansion process may be represented like this. This is the 2 dash. The state 2 dash is the state of the steam after actual expansion. Corresponding to that 2 dash, the enthalpy of the steam is H2 dash. That H2 dash given 2560 kilojoules per kg, 2560 kilojoules per kg. You are asked to decide the turbine efficiency. As we all know, the turbine efficiency equal to ratio between the actual turbine work and ideal turbine work. Are you following? Yes. Ratio between the actual turbine work and ideal turbine work is the turbine efficiency. But what is the actual turbine work? H1 minus H2 dash. That is the actual enthalpy drop. Okay. Similarly, ideal turbine work is ideal enthalpy drop. H1 is 3200 minus H2 dash 2560 dividing by 3200 minus H2 value 2400. You simplify this value for getting the turbine efficiency. It is equal to 3200 minus 2560, 40, right? 640. 640 dividing by, here it is 800. Of course, into 100 for getting in percentage. You simplify this value, 880. So finally answer is 80%. So turbine efficiency is 80%. Understood? Yes. Now look at the options. Look at the option B. Option B is absolutely correct. Okay. Similarly, look at the next question. These are all very, very important questions. Look at the next question. Try to read it clearly. What is the efficiency of an ideal regenerative Rankine cycle power plant using saturated steam at 327 degrees centigrade at a pressure of 135 bar at the inlet to the turbine and condensing temperature of 27 degrees centigrade corresponding to saturation pressure of 3.6 kilopascal. This problem connected to ideal regeneration cycle. as we all know, the efficiency of the ideal regeneration cycle is equal to Carnot cycle efficiency only. Carnot cycle efficiency depending on only two temperature limits, that is highest temperature of the cycle and lowest temperature of the cycle. First let me mark the highest temperature and lowest temperature. You need not to mark it because straight away temperatures are given. The T minimum given 27 degrees centigrade, that is equal to 300 Kelvin. Okay na? And T maximum, what is the T maximum? Maximum temperature is given 327 degrees centigrade, make it in Kelvin, is equal to 600 Kelvin. 600 Kelvin. Okay. Then what is the efficiency of the Carnot cycle? Efficiency of the ideal regeneration cycle. Efficiency of the ideal regeneration cycle is equal to efficiency of the Carnot cycle. Okay. It is equal to, what is the efficiency of the Carnot cycle? 1 minus minimum temperature dividing by maximum temperature. It is equal to 1 minus minimum temperature 300 dividing by maximum temperature 600. 300 by 600, 0.5. 1 minus 0.5, 0.5. So finally its efficiency equal to 50%. So that is efficiency of the ideal regeneration cycle. Look at the option C. Option C is absolutely correct. Understood? Remember this point. The ideal regeneration cycle efficiency for thermoelectric power plant is always equal to Carnot cycle efficiency, and Carnot cycle efficiency depending on only the minimum temperature of the cycle and maximum temperature of the cycle. But only the thing is, you need to take the minimum temperature and maximum temperature in Kelvin, that is absolute temperatures. Okay. Now let us move to the another question. Try to read it clearly. Try to read it. It is asked like this. In a simple gas turbine power plant operating on standard Brayton cycle, power needed to drive the compressor is 175 kilowatts. The power required for driving the compressor is, that means work required for compressor in 1 second is 175 kilowatts. Okay. Rate of heat supplied during the constant pressure heat addition process is 675 kilowatts. The heat supplied in 1 second is 675 kilowatts. Turbine output obtained during the expansion process is 425 kilowatts. Work output of the turbine in 1 second is 425 kilowatts. What is the rate of heat rejection during constant pressure heat rejection? You are asked to decide how much amount of heat is rejected in 1 second. That is the problem. Dear friends, it is given for the Brayton cycle because it is given simple gas turbine power plant. Simple gas turbine power plant is working on Brayton cycle. Anyhow, for any thermodynamic cycle, according to first law of thermodynamics, the cyclic integral del Q is equal to cyclic integral del W. That means net heat transfer is equal to net work transfer. Cyclic integral del Q means the net heat transfer is equal to net work transfer. Okay. Dear friends, remember the symbol cyclic integral is used for only thermodynamic cycle. The cyclic integral represents sum for a complete cycle. SUM, sum for a complete cycle. Anyhow, the net heat transfer means heat supplied minus heat rejection. And the net work output means the turbine work minus compression work. Okay. Now, what is the heat supplied given? Heat supplied given is 675. 675 minus heat rejection is equal to turbine work is 425, compression work is 175. 425 minus 175. Okay, you simplify this value. 420, of course it can be written like this. The amount of heat rejection is equal to 675 minus becomes plus 175 minus 425. You simplify this value. Here 675 plus 175, 675, 750, 850. 850 minus 425. What is the 850 minus 425? This is the value, half of this value. It means indirectly 425 kilowatts. That is the amount of heat rejecting from the simple gas turbine power plant. Look at the options. Look at the option B. Option B itself is absolutely correct. Are you following clearly? Yes. Now look at the another important question. Try to read it clearly. It is asked like this. In a simple single stage gas turbine plant, if T1 is the minimum temperature and T3 is the maximum temperature, then what is the work ratio in terms of pressure ratio? You are asked to decide work ratio in terms of pressure ratio and the temperature limiting ratio. Given that T1 is the minimum temperature and T3 be the maximum temperature. Okay. For this, it is better to project the temperature versus entropy coordinate system for the Brayton cycle. Temperature versus entropy coordinate system. The Brayton cycle consists of 4 processes: isentropic compression 1 to 2, isentropic compression followed by 2 to 3, constant pressure heat supplied 3 to 4, isentropic expansion followed by 4 to 1, constant pressure heat rejection. Okay. Now, as you know, for the process 1 to 2, that is isentropic compression process. For this isentropic compression process, the relation between the temperatures and pressures is T2 by T1 is equal to P2 by P1 power gamma minus 1 by gamma. Okay. P2 by the pressure after compression, P1 by the pressure before compression. That P2 by P1 we are marking as Rp power gamma minus 1 by gamma. Okay. Similarly, look at the 3 to 4 process. Look at the 3 to 4 process. 3 to 4 process is also isentropic process. It is also isentropic but expansion process. For this expansion process, I can write T3 by T4 equal to, it consists of only 2 pressure limits, that is pressure before compression, pressure after compression. Okay. Anyhow, T3 by T4 is equal to P2 by P1 power gamma minus 1 by gamma. But the quantity P2 by P1 generally written as pressure ratio Rp power gamma minus 1 by gamma. Okay. Now let us see the work ratio. Work ratio equal to ratio between the net work and turbine work. Here net work equal to what? The turbine work minus compression work dividing by turbine work. It is equal to 1 minus compression work dividing by turbine work. Okay. Now let me write the work formula for compressor. Work required for compressor equal to what? Since the compressor is working by reversible adiabatically, that too compressor is treated as a steady flow device. Reversible adiabatic steady flow work always equal to change in enthalpy of the working material. Once again, compressor is working by reversible adiabatically. That too, the compressor is coming under a steady flow device. Steady flow reversible adiabatic work always equal to change in enthalpy of the working material. Therefore, compression work equal to H2 minus H1. But what is the working material for our Brayton cycle or gas turbine power plant? Atmospheric air only. Atmospheric air is coming under one of the ideal gases. For any ideal gas, enthalpy is the function of only temperature. Therefore, it can be written as Cp into T2 minus T1. Because for any ideal gas, let me write that point. For any ideal gas, enthalpy is the function of only temperature. Okay. So this is the work required for compressor. Similarly, the turbine work. Turbine also steady flow device. That too it is working by reversible adiabatically. Reversible adiabatic steady flow work always equal to change in enthalpy of the working material. Therefore, turbine work equal to enthalpy at state 3 minus enthalpy at state 4. That means enthalpy before expansion minus enthalpy after expansion. It is like this, H3 minus H4. But enthalpy is the function of temperature only. It can be written as Cp into T3 minus T4. Okay. Now let me write this compressor work value and turbine work value in our relation. The 1 minus compression work is Cp into T2 minus T1 dividing by Cp into T3 minus T4. The Cp will be cancelled. The specified constant pressure is remaining same. It is equal to 1 minus, let me write the minimum temperature outside from the numerator. T1 into T2 by T1 minus 1. And from the denominator, T3 is the maximum temperature. Let me write the maximum temperature outside. It is 1 minus T4 by T3. Okay. Now, let me write the remaining part here. The work ratio is equal to 1 minus T minimum by T maximum into T2 by T1. What is the T2 by T1? Look at the T2 by T1. T2 by T1 is equal to Rp power gamma minus 1 by gamma. In the place of T2 by T1, I am writing Rp power gamma minus 1 by gamma minus 1 dividing by 1 minus T4 by T3. Look at the T3 by T4. T3 by T4 equal to Rp power gamma minus 1 by gamma. Then T4 by T3 equal to 1 by Rp power gamma minus 1 by gamma. So it is 1 minus 1 by Rp power gamma minus 1 by gamma. Okay. It is equal to 1 minus minimum temperature dividing by maximum temperature into Rp power gamma minus 1 by gamma minus 1 dividing by Rp power gamma minus 1 by gamma minus 1. Let me write it clearly. Your understanding is important. Rp power gamma minus 1 by gamma dividing by this part Rp power gamma minus 1 by gamma. So this part is cancelled. This part is cancelled. Finally it is 1 minus minimum temperature by maximum temperature. This Rp power gamma minus 1 by gamma goes up. Rp power gamma minus 1 by gamma. So that is the work ratio in terms of minimum temperature, maximum temperature and pressure ratio. Understood clearly? Yes. So work ratio 1 minus T1 by T3 into Rp power gamma minus 1 by gamma. Look at the options. Look at the option 1 minus T1 by T3 Rp power gamma minus 1 by gamma. Once again, let us go back to that one. 1 minus T1 by T3 Rp power gamma minus 1 by gamma. Yes. Option B is absolutely correct. Okay. This is very important question. This is 5-star question. Most expected question for the competitive exams. 5-star question. Okay. Shall I move to the next one? Yes. Look at the next question. Try to read it clearly. Mean temperature of heat addition gets increased, resulting in an increase in cycle thermal efficiency. What is this cycle called? You know, regeneration mechanism. Regeneration mechanism for thermoelectric power plant is for what? Increasing the feed water temperature. When I increase the feed water temperature with regeneration mechanism, the water can be entering to the boiler at high temperature. Since feed water can be entering to the boiler at high temperature, the mean temperature of heat addition is going to increase with regeneration type steam turbine power plant. It is like this. First let me mark the TS diagram for the simple cycle, temperature versus entropy diagram. For the simple cycle, let me mark the saturation dome, that is the saturation dome. The steam turbine power plant consists of only two pressure limits. Pressure before expansion, that is P1, and pressure after expansion can also be called as condenser pressure P2. Generally, we are allowing the superheated steam to the turbine. This may be the initial state. The steam is made to enter to the turbine to expand isentropically. That isentropic expansion can be marked like this. This is the 1 to 2 isentropic expansion. Okay. Followed by 2 to 3 condensation process, 3 to 4 isentropic pumping process, and 4 to 1. That means with state 4 temperature, the feed water is entering to the boiler. Then that feed water is becoming saturated liquid. Saturated liquid is becoming saturated vapor, and saturated vapor is becoming superheated vapor. Okay. Now for this simple cycle, the mean temperature of heat addition, may be 1 minute. The mean temperature of heat addition somewhere in between state 1 and state 4. The mean temperature of heat addition somewhere in between state 1 and state 4. This is the mean temperature of heat addition. Let it be Tm1. Okay. But with regeneration mechanism, what we are doing? We are extracting the steam before complete expansion. And that extracted steam is used for preheating the feed water. That is like this. Let us assume corresponding to pressure corresponding to, let this is the what P2 dash pressure, we are extracting a part of the steam. We are extracting a part of the steam for the purpose of preheating the feed water. That means assume 1 kg mass of steam is entering to the turbine. That 1 kg mass of steam is expanding up to state 2 dash. At state 2 dash, I am extracting m amount of steam, and that extracted steam is used for preheating the feed water. Then remaining 1 minus m quantity of the steam is expanding to state 2. There 1 minus m kg mass of steam is becoming 1 minus m kg mass of liquid during the condensation. That 1 minus m kg mass of liquid is boosted to this P2 dash pressure. Let this is the 3 dash. So at this 3 dash, this condensate is available corresponding to P2 dash, where the condensate available at state 3 dash and bled steam available at state 2 dash, that is m quantity of the steam, both are directly mixing. By the time this liquid available at state 3 is mixing with the m kg mass of steam, that m kg mass of steam is losing the latent heat. By the time m kg mass of steam is losing the latent heat, its temperature cannot be changed. But whatever the latent heat which is rejected by the m kg mass of steam is taken by this 1 minus m kg mass of liquid available at state 3 dash, that will be gaining its temperature. Finally, both are compromising somewhere at 3 double dash. By the time m kg mass of steam is losing the latent heat, its temperature cannot be changed. Whatever the latent heat which is given by the m kg mass of bled steam is taken by 1 minus m kg mass of liquid. Because of the receiving of 1 minus m kg mass of liquid in the form of sensible heat, its temperature increasing from 3 double dash temperature to 3 dash temperature to 3 double dash temperature. Understood? Then it is boosted to high pressure. Finally, look at the state where the water can be entering, with regeneration mechanism for thermoelectric power plant. So water can be entering with a temperature T4 dash. Then the average temperature or the mean temperature of heat addition between the state 1 and state 4 temperatures, the mean temperature of heat addition between the state 1 temperature and state 4 double dash temperature definitely above this Tm1 only. So this may be the mean temperature of heat addition, let it be Tm1 dash. That means from that you can say that with regeneration mechanism, the mean temperature of heat supplied that I mark as Tm1 increases. But the heat rejection, the total heat rejection is taking place at constant temperature. That temperature you can call as condensation temperature. Then what about the thermal efficiency? Thermal efficiency is equal to 1 minus condensation temperature dividing by mean temperature of heat addition. If this mean temperature of heat addition, let it be written clearly, this is the mean temperature of heat addition. So at constant condensation temperature, if the mean temperature of heat addition increases, this factor is decreasing. 1 minus decreasing value will increase the thermal efficiency. That is how the thermal efficiency of the thermoelectric power plant with regeneration mechanism increases due to increase in mean temperature of heat addition. Anyhow, with regeneration mechanism for thermoelectric power plant, the mean temperature of heat addition is increasing from Tm1 to Tm1 dash. Understood? Yes. Now look at the options. Anyhow, mean temperature of heat addition gets increased, resulting in an increase in cycle thermal efficiency. What is the cycle called? Definitely the cycle is called regenerative type cycle. Got that point? Yes. Now let us take the another important question. Try to read it. Try to read the question. In a two-stage reciprocating air compressor, the suction and delivery pressures, suction pressure, let it be P1, suction pressure PS equal to P1 equal to 1 bar, and delivery pressure for the two-stage compression, it is given for two-stage compression. For a two-stage compression, this delivery pressure equal to P3, that P3 equal to 4 bar. Respectively, for the maximum efficiency, the intercooler pressure, very easy, the intercooler pressure P2 equal to root under P1, P3. That is the optimum intercooler pressure for the best performance of the reciprocating compressor. It is equal to root under P1 is 1 bar into 4, 1 into 4, 4. So root under 4 equal to 2 bar. That is the optimum intercooler pressure. If you can construct the two-stage reciprocating compressor to cool the in the intercooler at this pressure, your compressor is demanding less work. Understood clearly? Anyhow, the optimum intercooler pressure is 2 bar. Understood clearly? Yes. Similarly, look at the another important question. Try to read it clearly. In a petrol engine, the tendency of knocking decreases with. For the petrol engine, you are asked to decide how the knocking tendency can be decreased. Option A, increase in charge temperature. Option B, increase in cylinder diameter. Option C, increase in compression ratio. Option D, decrease in atmospheric humidity. Dear friends, you know, in the atmospheric air, the amount of moisture present is very, very small. Since the amount of moisture present in the atmospheric air is very, very small, the humidity may not be affecting the detonation of the spark ignition engine. Therefore, D is not correct. Okay. Next, increase in compression ratio. When I increase the compression ratio, knocking for the SI engine increases. But it is asking what is the parameter causing decreasing the knocking of spark ignition engine. This petrol engine is also called spark ignition engine. Anyhow, when I increase the compression ratio, detonation increases or knocking increases. Therefore, C also not correct. Next, increase in cylinder diameter. When I increase the cylinder diameter or when I maintain the large size cylinder diameter, definitely the knocking increases. Now come to the increase in charge temperature. As we know, by the time the charge is entering to the engine cylinder, if it is maintaining high temperature, you take the summer air, you know, summer air is maintaining high temperature. In the summer season, I can say that the charge is entering to the petrol engine at high temperature. If the charge is entering to the petrol engine at high temperature, definitely the petrol particles can be quickly evaporating. If the petrol particles are quickly evaporating, that evaporated petrol vapor can be more uniformly spreading throughout the combustion chamber to maintain the homogeneous mixture. That is one of the reasons why the knocking decreases. On the other hand, once again, when the temperature of the heat at constant pressure, the slope of the constant pressure curve is T by Cp. The T by Cp is less than T by Cv because Cp is more than Cv. Okay? And to satisfy the condition, that is heat supplied for Otto cycle equal to heat supplied for diesel cycle, I extended the heat addition curve beyond the 3 to 4 because area below 2, 3, area below 23 is the heat supplied for Otto cycle. The heat supplied for Otto cycle must be equal to heat supplied for diesel cycle. For that, I am assuming that area below 2 dash 3 dash, area below 2 dash 3 dash will be equal to area below 2 3, because area below the TS diagram is equal to heat transfer. I hope you got my point. Once again, since area below the TS diagram is equal to heat transfer, heat supplied for Otto cycle must be equal to heat supplied for diesel cycle. What is the heat supplied for Otto cycle? Area below 2 3. What is the heat supplied for diesel cycle? Area below 2 dash 3 dash. Area below 2 dash 3 dash must be equal to area below 2 3. That's why I extended the constant pressure heat addition curve for diesel cycle beyond the 3 to 4. It means whatever the additional area the Otto cycle heat addition curve is maintaining in this region will be compensated by the diesel cycle heat addition curve in this particular region. Therefore, I am concluding that area below 2 dash 3 dash is equal to area below 2 3. Okay, followed by 3 dash 4 dash isentropic expansion for diesel cycle. 4 dash 1 dash is the heat rejection for diesel cycle. Okay, now 1 dash 2 dash 3 dash 4 dash 1 dash is the diesel cycle, is the diesel cycle. Okay, now for the Otto cycle, the heat rejection for Otto cycle equal to area, you know, 4-1 is the heat rejection curve for the Otto cycle. Area below 4-1 is the heat rejection for Otto cycle, whereas the heat rejection for diesel cycle, the heat rejection is represented as 4-1 dash for diesel cycle. Heat rejection for diesel cycle equal to area below 4-1 dash. Now you decide, is it area below 4-1 dash more than 4-1 or less than 4-1? Definitely area below 4-1 dash is more than area below 4-1. Therefore, I can conclude that heat rejection for diesel cycle is more than heat rejection for Otto cycle. Okay. Now, as you know, efficiency equal to what? 1 minus heat rejection by heat supplied. Isn't it? But it is given that the heat supplied for Otto cycle and heat supplied for diesel cycle both are identical. That means this heat supplied is arrested, because it is clearly given the heat supplied for Otto cycle equal to heat supplied for diesel cycle. That means heat supplied is arrested. If the heat supplied is arrested, the cycle which is rejecting less heat can maintain the better efficiency. Which cycle is maintaining less heat? Otto cycle is maintaining less heat rejection. Since Otto cycle is maintaining less heat rejection, definitely I can say that Otto cycle efficiency is more than diesel cycle efficiency. Is it understood? Yes. Now look at the options. The thermal efficiency of the Otto cycle is more than that of diesel cycle. Therefore, you can select the option B. Is it understood? Yes. Now look at the another question. Try to read this question. Spark ignition engine fuels in order for decreasing knocking tendency. For the petrol engine, the fuels for decreasing order of knocking tendency. Option A, paraffins, aromatics, naphthalenes. B, paraffins, naphthalenes, aromatics. Yes, option B is absolutely correct. This is the decreasing order of petrol fuels in terms of knocking. That means the knocking maintained by aromatics less than that of naphthalene, less than that of paraffins. Okay. Similarly, look at the another important question. Try to read this question. The big end bearing of the connecting rod of a reciprocating engine is always, dear friends, remember, the small end of the connecting rod is connected to piston by means of piston pin, is also called wrist pin, is also called gut joint pin, whereas big end of the connecting rod is connected to the crank by means of a pin. That pin is called crank pin. Once again, the big end of the connecting rod is connected to the crank by means of crank pin. That crank pin is basically a journal bearing, but that bearing is made to split into two parts. That journal bearing is made to split into two parts for easily inserting and for easily replacing. That's why that kind of bearing you may call as a bush bearing. The big end of the connecting rod is connected to the crank by means of a bearing called bush bearing. That means that crank pin is acting as a bush bearing. Okay. Similarly, look at another important question. Try to read it. The ignition coil in an automobile acts as a, in case of battery coil ignition system, a small battery is used for supplying the DC power with a voltage ranging from 6 to 12 volts only. But once the contact breakers are suddenly opening, the magnetic flux existing between the primary winding and secondary winding suddenly collapsing, then in the secondary winding side, what is the voltage of the spark available? That means what is the range of high voltage available in the secondary winding? 10,000 volts to 20,000 volts. Such a very huge voltage power is available in the secondary winding side. Look at the voltage increment. The voltage increment is suddenly happening. Therefore, that magneto-coil ignition system or battery coil ignition system is working in the same manner as step-up transformer because the voltage suddenly increasing. Therefore, I can select the option C. Got that point? Yes. Similarly, look at another important question. Try to read it. In combustion process, the effect of dissociation. Dear friends, remember, dissociation means disintegration of combustion products. The disintegration is coming under endothermic reaction. That endothermic reaction is absorbing the heat. Firing process is the exothermic reaction. During the exothermic reaction, heat is released. But the dissociation is also called disintegration. It is like this. The carbon dioxide, these are the combustion products, will be splitting into carbon monoxide and oxygen. For splitting the carbon dioxide into carbon monoxide and oxygen, it is absorbing the heat. Heat is absorbed. Because of the heat absorbed, what about the temperature of the gas? Definitely decreases. Look at the options. In combustion process, the effect of dissociation is to reduce the flame temperature. Therefore, option A can be selected. Why the flame temperature is reduced? Because of the heat absorption. Why the heat absorption is happening? The dissociation or disintegration process is coming under endothermic reaction. Endothermic reactions are absorbing the heat, whereas exothermic reactions are releasing the heat. It is like this. C plus O2. C plus O2 gives rise to CO2. This is the exothermic reaction. During the exothermic reaction, the heat is released. Heat is released. During the heat releasing process, the flame temperature increases. But dissociation is decreasing the flame temperature because of the heat absorption. Dear friends, remember, the disintegration or dissociation generally happening at high temperature. Understood clearly? Yes. Similarly, look at another important question. Try to read it. For the same maximum pressure and heat input. For the same maximum pressure and heat input, option A, the exhaust temperature of petrol engine is more than that of diesel engine. That is absolutely true. As you know, the diesel engines are maintaining better efficiency. The diesel engines are maintaining better thermal efficiency means what? More part of the heat energy will be converted to work energy. By the time more part of the heat energy is converted to work energy in the diesel engine, the exhaust gas are trying to leave from the diesel engine at low temperature. But in the petrol engine thermal efficiency is less. Petrol engine thermal efficiency less means only less part of the heat released will be converted to work energy. By the time less part of the heat energy is converted to work energy in the petrol engine, the exhaust gases are trying to leave from the petrol engine at high temperature. Got that point? Once again, for the same maximum pressure and heat input, the exhaust temperature of the petrol engine is more than that of diesel engine. Option A is absolutely correct. Understood? Yes. Similarly, look at the another important question. Try to read it. The essential function of the carburetor in a spark ignition engine is. The main function of the carburetor in the spark ignition engine, that is petrol engine, is. Option A, meter the fuel into the air stream and amount dictated by the load and speed. Absolutely correct. The carburetor tries to supply required quantity of the air fuel mixture based on the load and speed of the engine. Similarly, look at the B. Bring about mixing of air and fuel to get a homogeneous mixture. It is also looking correct. Vaporize the fuel. Yes, petrol is vaporizing. That is also correct. D. Distribute the fuel uniformly to all cylinders in multi-cylinder engine and also vaporize it. It is also looking correct. All are looking correct. But is asking the essential function, the main function. All are absolutely correct. All are connected to carburetor. All these functions are done by the carburetor. But most essential function is, right, it is supplying the correct quantity means meter the fuel into means correct quantity of air fuel ratio can be, right, correct quantity of air fuel ratio should be supplied for the petrol engine based on the load on the engine and speed of the engine. Therefore, the most essential function of the carburetor is to supply the required quantity of the air fuel ratio based on the load and speed of the engine. Understood? Similarly, look at the another important problem. Try to read it. The object of providing masked inlet valve in the air passage of the compression ignition engine. Compression ignition engine means diesel engines. CI engines means diesel engines. Generally, for the diesel engines, the inlet valve is masked. Once the inlet valve is masking, the air is made to enter at an angle. That air entering to the cylinder at an angle is meeting the edge of the cylinder, causing some swirl motion. Turbulence is compulsory. The turbulent motion is compulsory for diesel engine for effective mixing of the diesel particles which are injected at the end of the compression process. For that, the diesel engine combustion chambers are constructed such that to maintain some rotary motion called turbulent motion. Anyhow, to have the turbulent motion, the inlet valve is masking. Once the inlet valve is masking, the air is made to enter to the cylinder at an angle. That entering air is touching the edge of the cylinder, causing some swirl motion. Anyhow, the object of providing masked inlet valve in the passage for the air passage for the compression ignition engine is to produce the pre-vol during the suction stroke, that is induced primary swirl. Is it understood clearly? To produce the induced primary swirl, the inlet valve is masked. Similarly, look at the Another important question. Try to read that question. Brake thermal efficiency of the three types of reciprocating engine commonly used in road vehicles are given in the increasing order. Dear friends, remember the increasing order of thermal efficiency is like this. Thermal efficiency maintained by brake thermal efficiency, let me write it clearly. Brake thermal efficiency maintained by two-stroke petrol engines is more than brake thermal efficiency maintained by two-stroke diesel engines more than brake thermal efficiency maintained by four-stroke petrol engines more than brake thermal efficiency maintained by four-stroke diesel engines. From that, right, from that I can conclude that four-stroke diesel engines, 1 minute, two-stroke petrol engine, two-stroke diesel engine, four-stroke petrol engine, four-stroke diesel. Let me write it clearly. Your understanding is important. Four-stroke diesel engine, four-stroke diesel engine. Okay. The reason why the two-stroke engines are maintaining less efficiency than four-stroke engines is, as we all know, in case of two-stroke engines, there is a port mechanism. The ports are opening and closing by only piston movement. Since the inlet port and outlet port both are opening and closing by piston movement only, in a particular period of time, the exhaust port and transfer port both are opening. Once the exhaust port and transfer port are opening, due to downward movement of the piston, the fresh charge available from the transfer port may be escaping along with the exhaust gas. That means the fresh charge escaping rate is more in the two-stroke engines compared to four-stroke engines. Because of that, generally means, right, brake thermal efficiency of two-stroke engines always less than 1 minute. This is sorry, 1 minute, sorry. This is less, sorry. 1 minute, less. Printing mistake. Less than. The reason is, in case of two-stroke engines, some fresh charge is always trying to escape. Once some fresh charge is trying to escape along with the exhaust gas, if it is petrol engine, petrol is also escaping. Since petrol is also escaping along with the exhaust gas in case of two-stroke engines, right, the two-stroke petrol engine efficiency less than that of the two-stroke diesel engine. Why the two-stroke diesel engine efficiency more? Though some fresh charge is escaping along with the exhaust gases, that fresh charge is only air. That means fuel cannot be escaping in case of diesel engines. If you compare the petrol engines and diesel engines, the petrol engine efficiency is less than diesel engine efficiency. Even if it is four-stroke engine, because of the valve overlapping, there is a chance to escape some fresh charge. That fresh charge is the only air in case of diesel engine. But that fresh charge is mixture of air and petrol particles for the petrol engine. That's why some petrol is always escaping or some fuel is always escaping in petrol engine, whether that petrol engine is either two-stroke type or four-stroke type. That's why if you compare the diesel engine and petrol engine, definitely the petrol engine thermal efficiency is less than diesel engine efficiency. On the other hand, if you compare the two-stroke engines and four-stroke engines, the thermal efficiency of the two-stroke engines is less than that of four-stroke engines. From this, you can conclude that the two-stroke petrol engine efficiency less than the two-stroke diesel engine efficiency less than the four-stroke petrol engine efficiency less than four-stroke diesel engine efficiency. I hope all of you clearly understood. Now let us take the options. Brake thermal efficiency of the three types of reciprocating engine commonly used in road vehicles are given in the increasing order. Two-stroke SI engine, 4-stroke SI engine, 4-stroke CI engine. Absolutely correct. This is the order, increasing order. Is it understood clearly? Yes. With this, my dear friends, I am concluding today's class. Day after tomorrow, that is on 26th December, we will discuss the most expected questions for the last part of the thermal engineering, that is refrigeration and air conditioning. I hope all of you clearly understood. God bless you. Right? Have a nice day. Good night. Bye.
From Civil Engineering discipline. For prelims preparation, I took online test series from ACE online platform and used to regularly solve their subject-wise test and full-length test. Then for mains preparation, I solved question banks which were given to me as a part of mains postal program from ACE Online. And then last but not the least, for interview preparation, I followed the interview guidance material which was given to me as a part of ACE Online's interview guidance program.
I am Vinit Kumar. I have secured All India Rank 1 in Mechanical Engineering in ESC 2021. I have been associated with ACE Engineering. I have taken various programs like Lives, main classes, postal study course, test series and interview guidance program. So would like to thank all the faculties of ACE. It has helped me in building my concepts and having my fundamentals cleared. I would also like to highlight that in test series, I have given various mock tests which have helped me in the time of real exam, and in interview guidance program, building confidence in front of